Balanced job bounds. So we already saw one set of bounds which were asymptotic bounds, and that gave us the upper bounds on throughput and lower bounds on response time. So sometimes we want the other way around. And for that, we have balanced job bounds. So a balanced system is a system which has no bottleneck. What that means is that all the devices have equal utilization. Everything could be 90% highly utilized, but that is a balanced system. As long as utilization of 1 is equal to utilization of 2 equal to utilization of 3, right? So now in that system, if you want to fix anything, you really have to fix everything, not just one thing, which in sense is good because that is the system you want, a balanced system. A balanced system has a better performance than any unbalanced system, a similar unbalanced system. So let's see what similar means in a minute. But by this method, we can get both the lower and the upper bound. Now, this is based upon this observation that an unbalanced system can always be improved by replacing the bottleneck device with a faster device. So if you have an unbalanced system where all the utilizations are not equal, which means all the demands are not equal, all you have to do is take the bottleneck, make it faster. Right? So we'll do that. And before we hear the final result that you will get anyway at the end, and so these are the bounds, that the response time has to be more than this and less than this. So you have two-sided bound on the response time and two-sided bounds on throughput. Throughput has to be more than this and less than this. So the purpose of presenting these two formulas first is to just explain to you some of the terms. N is the number of users. D max is the bottleneck demand. So you have D1, D2, D3. D max is the maximum of those two. Z is the think time. Capital D is the sum of all the demands. So if you add up D1, D2, D3 up to D max, you get capital D. N minus 1 times D average. D average is basically D upon M. D is the total sum. You divide by the number of devices, you get D average. Then D upon D plus Z, and everything else is standard, same terms. So as long as you understand D max, D average, and capital D, we can go on to the next slide. So basically D average is D upon M, where D is the sum. And these bounds are very tight. Tight in the sense that when we'll see the plot, we will see that they're very close. Okay? And upper and lower bounds are very close. For batch systems, the bounds can be optimized substituting Z equal to 0. If there are no think time there, then you can just put Z equal to 0 and you get a similar bound. So basically, the assumption is that all service centers except the terminals are fixed capacity service centers. So that is one thing which is assumed. Basically, it assumes that central server model that we talked about earlier. And the terminals are represented by delay centers, just like we talked about for the central service model, and there are no other delay models. This one, actually, this particular expression has been derived for the central server model. If you have a different model, then you will have to probably derive something different, and we will show you how to derive these things. The derivation is 3 steps. First is you derive the throughput and the response time of a balanced system. How? Given an unbalanced system, construct a corresponding best balanced system such that the number of devices is the same, total demand is the same, and this will produce the upper bound. So let's think about it one more time. So we know that, let's say we know that we need 4 seconds, 3 seconds, and 2 seconds. 3 devices. Total is 4 plus 3 plus 2 is 9. For 3 devices, we have 9 seconds of demand. Now, if we construct another system in which each device has 3 seconds of demand, so total is still 9, but that system will have better performance because we have now we have improved the bottleneck. Now, the question is, you can ask as to how come, we have also changed the other devices. Well, what we have done is, this is how you proceed. You take the most used device, which is the bottleneck, and you use the least used device. Okay. When you reduce the bottleneck by any amount, let's say by 1 second, and you increase this by 1 second, the effect of bottleneck will be much more than the effect of increasing the demand on the least utilized device. When you increase the demand on the least utilized device, the true performance will go down. I mean, in some sense, right? Very little though. You won't even notice. But this will have big effect. And you keep doing this until they're equal. Okay. If something else becomes highest and lowest, you just keep doing this until everything is equal. Okay. So it is given that if you do this balancing like this, where everything has equal demand and the sum is still the same, so we are not changing the sum, that system will have better performance than any of the unbalanced systems that we have constructed. Yeah, because utilization is proportional to demand. This is one thing we learned in this class, is UI is equal to X DI. Right? X is the system throughput, DI is the ith demand, ith device demand, and UI is the ith device utilization. So basically, the utilization is proportional to the demand, total demand. We are taking whatever numbers there are, we're taking the highest and the lowest and moving them. We are not, all we are doing is, in this example that you just took, the visit ratios are all 1. Because if something comes in once on the first job, it will go to the second job and the third, it will go to the second station and third station. You agree? In your system. Okay. Now, if I know the service time, when you come to this, I'm not even asking the arrival rate. When you get the service time on this one, and service time on this 4, and service time on the second one is 3, and the service time on the third one is 2. So the total demand is 4, 3, and 2. You agree? So that is all we need. And actually it turns out the arrival rate doesn't change because of the bottleneck. What is happening is, if the arrival rate is more than the bottleneck service time, then there will be infinite queue, and we are not even analyzing that system. So let's say that the arrival rate is less than 1/4. If the bottleneck is 4 seconds per job, we cannot service more than 1/4 jobs per second. So let's say it is 1/5 or something, right? So everybody will get 1/5. We are not changing arrival. We are just changing the actual total demand, which could be done by 2 methods, which could be done by changing the visit ratio. How do you change the visit ratio? By putting caches, or something else, so that you don't have to go to the device. That will change the visit ratio. Or by changing the service time. SVI. S times VI is DI. So you either change S or you change V. All right, so we are constructing a balanced system, and that system will give you the upper bounds on the performance, means highest performance, means highest throughput and the lowest response time, both. Okay. Then we similarly construct a worst case balance system such that each device has a demand equal to the bottleneck. But we change the number of devices so that the sum remains the same. Now we make the devices slow, but we remove some of the devices so that the sum remains the same. Okay. So this gives you lower performance. And if you do these two, then actually I already gave you this example. So let's go over this example. This is not 4, 3, 2, but it is 2, 3, and 1 with Z equal to 4. So the sum of the demands is 2 plus 3 plus 1 is 6. D average is 2. D max is 3. Maximum of 2, 3, and 1 is 2. So now the balance job bounds, you can put all the numbers as we said, D average, and so on and so forth. And you can plot them, and you can see that this is the lower bound and this is the upper bound dotted lines, and the solid line is mean value analysis. All right. Similarly, this is the lower bound, this is the upper bound, and the solid line is this one. And so you can see it is very close. If you get these two, then you don't have to do too much analysis. And this you can do without any iteration. The interesting thing is that you don't need iteration. For mean value analysis, you need iteration. You go to 49 and 50 and then 60, row by row. Here, you just program this formula and you can get the whole graph. And this is actually better than asymptotic bound, because asymptotic bound, the response time would be here, horizontal, where it is, right, it is giving you a higher limit here. All right. What else? So this is the balance gap bound basically. And what is happening is, well, this is just the Excel worksheet. The Excel worksheet is showing you the MVA value, which you do iteration by iteration, and then you can do the balance gap bounds from the formula, and then you can plot them. And you will see the same graph that I showed you a minute ago. We did actually 3 things in this chapter. First, we did an open queue with MM1 and some MM infinity. Yeah, the terminals were represented as MM infinity, means there was no queue. When you come, exponential arrival, exponential service time, and you're out. So that was infinity, and everything else was MM1. So that is the series queue. First we did the exact analysis of the serial queue, then we did for MVA, which is for closed networks. And then we said that you can, given the performance for n-1 users, you can get it for n. So we do row by row, find out the queue for n-1, and then go to n. That was it. And then finally we did the balance job bounds. In the balance job bounds, we find 2 systems, one with D average and one with D max. And then we write down the performance for those. All right. So this is a practice exercise for that. Homework 34A, write down the expression for balance job bounds and the system throughput for the data of homework 34A. By the way, there is no 34B. So this is 34C, and 34A, you can look up faster in your handout as to what 34A is. But basically the same thing that you did MVA, now you're going to add balance job bounds. Now we move on to a whole new thing. So this is the end of queuing theory.